Okay, so welcome to the 8th webinar series of the Department of Land Management, Faculty of Agriculture, University Putra, Malaysia. So I'm Arina, the moderator for today's session. Okay, so with us today is Dr. Samsuri Abd Wahid. Okay, so he is going to deliver the seminar for today. Okay, the webinar for today. So before we begin with Dr. Samsuri, let me introduce him a brief introduction. Okay, let me give a brief introduction about Dr. Samsuri. Dr. Samsuri Abd Wahid graduated with a Bachelor of Science Honours in Agriculture, Food and Environmental Chemistry from University of Glasgow, Scotland. He then pursued his master and doctorate degrees in agronomy at Colorado State University, Fort Collins, Colorado, USA. And he has more than 20 years of experience in teaching and doing research in the field of soil chemistry and environmental soil science. He also has authored and co-authored over 100 research articles in various journals. In the past few years, his research topics focus on the utilization of biochars produced from agricultural wastes for soil application as well as for environmental protection. Okay. So without further ado, let us welcome Dr. Samsuri Abd Wahid to deliver his webinar entitled Soil Chemistry Primer for Soil Managers. So please welcome Dr. Samsuri.
Okay, thank you very much, Dr. Rina. Assalamualaikum and very good morning to everybody. First of all, I would like to thank Dr. Rina and the unit of the industrial networking and also the community of Faculty Pertanian for making it possible for to me to deliver this seminar. And then I would like to welcome everybody to my webinar, especially my former postgraduate student that I can see from the list, Dr. Salim Sarki from Pakistan, Dr. Allah Hassan Fahmi from Iraq, and also Dr. Tariq from Kurdistan. Okay, the title of my webinar today is Soil Chemistry Primer for Soil Managers. So as the title suggests, I'm going to talk about the basic concepts in soil chemistry, okay? And it also means that I'm not going to cover the more advanced topics or advanced concept in soil chemistry, such as the electrochemistry, the electrical double layer, the redox chemistry, and so on. So to me, what I'm going to cover today is the knowledge, the basic knowledge in soil chemistry that must be understood by those involved in soil science, as well as a person who are interested in learning about soil. I don't think the concept is difficult to understand. So hopefully by the end of this webinar, at least you get some knowledge for those who are interested in soil science to know more about soil chemistry and the process involved in soil chemistry. Okay. Okay, let me start by introducing for the benefit of the students who are in this audience. So I would like to suggest some of the textbook in soil chemistry. So first of all, I would like to suggest everybody to read the introductory text in soil science, such as those written by Will and Brady, The Nature and Properties of Soil. So basically, this is the textbook that we use in our basic soil science class, okay? And then to go deeper in soil chemistry, the first book that I suggest is the introductory text in soil chemistry, written by Prof. Tan Kim He of Georgia, the late Prof. Tan Kim He of Georgia State University. It's called The Principle of Soil Chemistry. And then you can go deeper, which is an intermediate textbook in soil chemistry. One of those books that I suggest is the one written by Strawn et al. The title is Soil Chemistry. Okay, this is a more advanced, introduce a more advanced concept of soil chemistry, but you don't actually require advanced knowledge. You should be able to understand if you at least we have a what do you call a class in chemistry during your undergraduate. But for the more advanced textbook, so I call it textbook because it is not specialized. It is a general textbook in soil chemistry. So one is written by Donald Sparks at University of Delaware and C. Becker. So the title is Environmental Soil Chemistry. And then Garrison Esposito, this is more advanced because it's covered a lot of physical chemistry. So it's called the Chemistry of Soil. And then a book written by Professor McBride of Cornell. The title is Environmental Chemistry of Soils. Okay, so these are the textbook in soil chemistry. If you are interested to specialize or to research deeper in soil chemistry. Okay, and then so this is my presentation outline. So for the benefit of those who are interested in soil but have little knowledge in soil, so I'm going to introduce a little bit about the soil and its function. And then I'm going to talk on soil mineralogy because this is important because it builds up the momentum to understand the soil, the processes in soil. And then the source of charge on soil particles, how soil particle having a charge, and then related to the charge of soil particles, I'm going to cover on soil cation exchange capacity, soil buffering capacity, as well as soil pH. And then I'm going to talk about soil chemical properties and plant nutrition. And if I have time, so I'm going to talk about the relationship between soil chemistry and pollution control because I know somebody would be interested in the environmental side of soil chemistry because I can see from the list there are some in the environmental industries. Okay, so what is soil? Basically, for those who are not familiar with soil, so the most the most acceptable or the most used definition of a soil is the. I think I should make it big. Okay. Uh, the definition of soil, it is the unconsolidated mineral and organic materials on the immediate surface of the earth that serve as a natural medium for the growth of land plant. So this is basically what we use to define soil. So from this definition, we know that the soil consists of unconsolidated. So meaning the rocks are not soil, right? So it must be unconsolidated due to the weathering process and so on before we can call it as a soil. Okay, so these are some of the functions of soil. Some of it we can we can appreciate the function. We know the function, but some of these function it is very difficult to appreciate, right? So, for example, I give you a few examples. Okay, we know the soil and plant growth. So this, you don't have to study soil science to appreciate this. Everybody knows that soil have a relationship with plant growth. So it is a physical support of plants. So it provides water and plant nutrients. Okay, and then the essential element in plants. So everybody in soil science or in agriculture knows that we have two types of essential elements. One we call it as macronutrients, and the other one is micronutrients. So macronutrients and micronutrients uh, are not how to say are not defined by the amount of the nutrients in the soil, but rather by the amount required by the plant. So meaning that macronutrients are nutrients that are required in large quantities by the plant, while micronutrients are nutrients that require in minute quantity a plant, right? So, okay, I'm not going to talk about the function of macro and micronutrients. So, because I have to cover a lot of things here. Okay, and then soil as carbon and nutrient recycler. So, animal and plant biomass that are added to the soil are degraded by the soil microbes, right? And then during the degradation process, we have excess nutrients in the organic form. It will be returned to the soil in a process that we call that we term as mineralization. Okay, and then this nutrient can be taken up by the plant. Hence, soil can act as a recycler of nutrients. Okay, something is taken up by from the soil, and then as the plant dies and it decomposes and return back the nutrient to the soil. So that is why we can consider a soil as a carbon and nutrient recycler. But however, something that we have to remember that everything have carrying capacities, right? So meaning that there are limits to certain things. Okay. So soil as well. So we cannot, even though it is a nutrient recycler and it can absorb a lot of things, but it also have a carrying capacities. Okay. This is what we should consider when we want to apply or we want to dispose things to the soil. So waste disposal, soils as waste disposal. So uh, we might argue what is the age of human population, the modern human population. Some argues that the human population have been on this earth for more than 100,000 of years, right? So just remember, so how much waste that we have put on the soil. So can you see a lot of waste nowadays? So most of them have been decomposed, right? So that is why soil is a very important medium for waste disposal. So we put in anthropogenic input to soil include those the non-toxic and toxic substances, right? And then we have to remember that when God made certain microbes, soil microbe, for example, right? They come with a set of how to say it? A set of hormones, okay, that are only capable of decomposing simple materials, right? But when human beings put in chemicals that have never been seen by the microbe, for example, right? So the microbe have to mutate to produce that hormones to decompose. So we have to remember that some of these anthropogenic substances that we put in can be degraded and some of those cannot be degraded. So some compound that can be degraded, microbe can use it and it can be mineralized. Okay, but some others are very recalcitrant. So meaning they stay in the soil environment for a very long time. Okay, a group of chemicals that we call a persistent organic pollutants, the PEP. Okay, the term used by the United Nations Environmental Program. So they used to be called the dirty dozen. So meaning that there are 12 of them. There were 12 of them. But now it's already been 26 persistent organic pollutants listed by United Nations Environmental Program. So the groups of these chemicals, they have the following characteristic. They are very toxic to human and wildlife. So they can last for many years in the environment before degradation, okay, into less dangerous form. So that is why we call it as a persistent organic pollutants. And they can bioaccumulate in the food chain. They can be transported over long distances through air and water. Why? Because they are persistent in the soil environment and also in the air and in water environment. So just imagine some of the toxic chemicals that have been used by the American soldiers in Vietnam, right? So as a desiccant for the how to say it? They want to see where the Viet Cong, the Vietnamese armies, live or stays underground. So they have to desiccate all the trees and all the shrubs. Okay, those chemicals that are used during the Vietnam War, they are still there in the soil environment up to now. So if you go to the museum, right, to the Vietnamese War Museum, you can see all the you can see pictures of those of incidences that involve those chemicals, right? Okay. Now, for a basic soil study, so what is the basic soil study? The first is to understand soil variabilities. So soil is a very heterogeneous media, right? So to illustrate the heterogeneity of the soil, so we just have a ISAF conference. Okay, during the conference, our faculty member, Dr. Tan, our department member, Dr. Tan Ngai Ping, delivered a oral presentation on urea utilization in acid soil in oil palm plantation. And then after his presentation, Prof. Biswak from India, so he's the president of Indian Society of Soil Science, he commented that in acid soil, there is no possibility for urea to utilize, right? That is true based on the chemical principle. Because for urea to be volatilized, the ammonium should react with hydroxyl groups, right? Should react with hydroxyl group. So meaning that the pH should be high. The soil pH should be high. So that is why he said it's not possible to have a urea volatilization at high pH. At low pH. But the problem that one of the plausible explanation that scientists have come out with is in soils, there exist microsites. Even though soil pH is low, but there are sites, microsites, small sites in a soil that can have high pH. That is why many studies have shown that urea volatilization are possible to occur in low pH soil, or meaning that acidic soil. So that is just to illustrate the variability of the soil. Okay, and then study and understand the physical, chemical, and biological properties. Okay, so this is what I'm going to do today. I'm going to discuss on the chemical properties of the soil, and then relate soil characteristics to various land uses, and lastly, to classify soil for appropriate management practices. This is basic soil studies. Okay, okay, I'm going to start with paramaterials. Wow, it's already 20 minutes past. So minerals and organic matter. So we have mineral soils and also we have organic soils, right? So meaning that, but most soils are composed of mineral plus organic matter, okay? And then some soil coming from a deposited or transport paraminerals, and some paraminerals are in situ, meaning that it's weathered from the rock down below, right? And we have three types of rock: the igneous rock, sedimentary, and metamorphic rocks. And also, the rocks are composed of minerals. So, because I want to build up on the clay silicates, so I have to talk about the minerals. So, for minerals, we have the primary minerals, which are formed from the cooling of magma and lava. So, meaning that it comes from the cooling process of the magma and lava. That is the primary minerals. And the secondary minerals, they are not formed from the cooling process of magma and lava, but they are formed from the weathering process of the primary minerals. So these are where the clay silicates coming from. Okay, and then common mineral in soil. So we talk about the primary minerals. Those minerals form during the cooling process of magma and lava. So the examples are quartz, right? Sand particles, quartz, olivine, amphibole, pyroxene, and feldspar. These are primary minerals. And then for secondary minerals, meaning that minerals that are formed later due to the cooling process, during to the weathering process of primary minerals, are the important one are the clay silicates, and we also have gypsum, carbonates, limes, and also the oxides. Okay, now I'm going to talk about the soil colloids. So if you read textbook, they are always talking about soil colloids, right? So what are the soil colloids? So why they are important? So most chemical processes occur on soil colloids. Why? For two reasons. One is because high surface area per unit volume. So meaning they are very small, but they have high specific space area. Okay, that is high space surface area per unit volume, and they are also contain they also contain charge. So either positive or negative or both, right? So circles are very tiny particles we cannot be observed by naked eyes. So meaning that we put salt in water, so you can see there are the water is murky or cloudy. So this is because the existence of salt colloids and not affected so much by the gravitational force. So, and the size is less than 1 micron. So, the size of clay are those particles less than 2 micron. So, meaning that the salt colloid is much smaller than that, which is 1 micron. Sorry. Okay, salt colloids are mainly clay minerals. So, other minerals that we considered as salt colloids are the iron and aluminum oxide, which collectively we call it as square oxides. And there are also organic colloids. Okay, so if you are interested in studying the soil colloids, so these four guys, the Jacquin, Landa, Wove, and Van Overbeek, they have developed a theory to explain the colloidal suspension stability. So as a result of the interaction between the van der Waals force and also the electrostatic repulsion, which is the electrical double layer. If you study deeper in soil chemistry, you will know about it. So although this is not very important, I wouldn't say it's not important in soil science, but difficult to understand the application of it. But in, for example, in the waste, okay, in the waste treatment industries, for example, in uh, freshwater plant, right? The freshwater plant. So they have to put in aluminum and also iron substance, iron compounds to coagulate the colloids or the suspended particles in salt. So if they put too much, then it's going to be how to say it's going to contaminate the fresh water that we drink. Okay, our drinking water. If they put too little, then there is no coagulation. So this is where the DLVO theory comes, uh, uh, or where the DLVO theory can be used. So just imagine one day, if you go, if you wake up and then you open your fridge and you see your Coke, your Coca-Cola, the drink, are all transparent, and then you see how to get a brown precipitation at the bottom, right? So is it possible? It is possible if the scientists, the food scientists, didn't do well in how to say it, in creating or in developing the formula to keep the particles in suspension, because those, for example, those suspension, the black coke water that we see is actually, there is a suspension. If you don't believe me, you can filter it through the what do you call it, the membrane filter. Okay, the membrane filter, you can filter it out. Okay, so this is where the LVO theory can be used. So when we talk about the clay minerals, wow, times fly. When we talk about the clay minerals, so clay minerals are very small particles. Okay, remain in suspension in very long time, and it has a very high specific space area. And then the properties, the physical properties, the wet clay is very sticky and plastic. So the Teton Dam failure in July 1976, which killed thousands of people. So this is the result of the engineers who built the dam. Instead of using clay, they use what do you call, silt, right? They replace silt. They replace the clay with silt. So and the silt doesn't have this plasticity properties. So it caused the collapse of the Grand Teton Dam, okay, which were put on the Colorado River in, if I'm not mistaken, in Nevada. Okay, and then, okay, let's talk about the clay mineralogy. The basic unit of clay minerals are the silicon tetrahedra and also aluminum or magnesium octahedra. This is the most basic unit of clay minerals. So sometime in textbook, if you see uh, dioctahedra and trioctahedra, it refers to the aluminum and magnesium. If the majority of the how to say, the clay minerals is made up of aluminum, so it is called a dioctahedra. Okay, while if magnesium dominates the clay minerals, it is called a trioctahedra. Okay, so clay types depend on the arrangement of the silicon tetrahedral layer and also the aluminum magnesium octahedral layer. So there are three types of clay minerals, or some textbook they group it into two groups. First is a 1-to-1 clay, and then the second one is 2-to-1 clay, and the last one is 2-to-1-to-1 clay. So what are the differences? So 1-to-1 clay is made up of one tetrahedral layer. So let's go back. So this silicon tetrahedra unit will combine with another silicon tetrahedra unit. So it will make up the silicon tetrahedral layer. And similarly, the aluminum will be attached to another unit of aluminum or magnesium octahedra, and it become a octahedral layer. So meaning that the one-to-one type clay is made up of one tetrahedral layer and one octahedral layer. So the 2-to-1 clay type are made up of two tetrahedral layer and sandwiched in between one aluminum octahedral layer. So I will talk about 2-to-1 clay later. Okay, these are the diagrams of 1-to-1 type clay. So the example is kaolinite. So it consists of one silicon tetrahedral layer and one aluminum tetrahedral layer. And then at the bottom is an example of clay minerals, elite clay, montmorillonite. So two tetrahedral layer, and in between there is one aluminum octahedral layer. So let's see, let's look about the properties of some of these clays. Yeah. So 1-to-1 type clay, for example, the kaolinite, it is a non-swelling clays. Okay. Non-swelling clays. Why it is a non-swelling? Because there is a strong hydrogen bond between the interlayer spaces. And then we have 2-to-1 type clay. It is a non-swelling clays as well. Why? Because in between there is a potassium. There are potassium ions. So which how to say it form electrostatic force between the layers and the other layers. So in sandwich between these two layers are the potassium ions, potassium cations. And then another example is a 2-to-1 clay, a smeg type, which is highly expensive. So meaning that it can expand, right? So in between, it consists of water and cation. So why I show this diagram, because this is important when we talk about the CEC later. Okay, this is an example of 2-to-1 type clay, right? This is an example of 2-to-1 type clay. So it is a chloride minerals. Okay, we have this unit. I want to see. Sorry. So this silicon tetrahedra, this is silicon tetrahedra, and in between is aluminum octahedra. So in between two unit cells of the chloride minerals, there is one other minerals which we call as a brucite, right? Which is a brucite. So brucite have a positive charge. Okay. So in smeg type, in elite, we have potassium in between the unit layers, but in case of chloride, we have a brucite mineral which is positively charged. So the okay, I cannot talk much because the limiting time. Okay, clay mineral in soil depend on the extent of weathering of the soil that have gone through. So what types of mineral is determined by the weathering process of that area. Okay, so sources of charge in soil. Okay, this is important. So there are two sources of charge on soil colloids. The first one is the isomorphous substitution. So what is isomorphous substitution? Is a cation uh, of lower valency is replacing the cation of higher valency. For example, iron 3 plus replacing silicon 4 plus in the silicon tetrahedral layer. So what is the result of this isomorphous substitution is it will cause the clay minerals to have net negative charge. It will cause the mineral to have the clay mineral to have a net negative charge. Okay, this is an example. Okay, this is octahedral sheet. Okay, this is octahedral sheet. Just showing example of the octahedral sheet, right? Okay, in this case, there is no isomorphous substitution, so the net charge is zero. But imagine one of aluminium, okay, one of the aluminium in the octahedral layer is replaced by the magnesium, which have two charge. So meaning that instead of we have instead of having the original six charge, we have now only five positive charge. So the result is we will be having a net of negative one charge. Okay, this is just a basic illustration, but actually the number of charge, it probably it can be 0.67 mole and all that. I'm not going to go into detail into that. This is just the illustration on of how clay minerals can become charged. Okay, isomorphous substitution only occurs in 2-to-1 type clay. Okay, when there is an isomorphous substitution, there is a net negative charge on the surface of the clay. There is no isomorphous substitution in 1-to-1 type clay, right? Okay, and also another source of charge is the pH dependent charge. So this occurs on 1-to-1 type clay, which I mentioned earlier. There is no isomorphous substitution. So meaning that there is no permanent charge of 1-to-1 type clay. It's only pH dependent charge. Okay, in 1-to-1 type clay and also in humic materials. Okay, the 1-to-1 type clay and humic materials contain surface functional groups, which this functional group can become positively charged, negatively charged, or no charge, depending on the pH of the salt solution. Okay, depending on the pH of the salt solution. This is an example of how they become charged and have no charge. For example, at pH of less than 5.5, we will have a net positive charge, while between pH 5.5 to pH 7.5 there is no charge, and above 7.5 we have a net two negative charges, right? So this is how the pH dependent charge works on the 1-to-1 type clay and also on the organic materials. So this is how to say it? The schematic diagrams of organic materials and salt, and you can see that we have a lot of functional groups, right? A lot of functional groups. For example, we have the carboxylate groups, we have the hydroxyl groups, okay, we have the amine group, we have the carbonyl groups. So all these functional groups uh, can be positively charged, negatively charged, or no charge depending on the salt pH. Okay. Now, if we talk about the charge in the soil, so we have to know about the cation exchange capacity. Why it is important? So the cation exchange capacity, or the acronym is CEC, is a soil properties that can give us an idea of the charges of the soil colloids, and more importantly, the ability of the soil to retain nutrients as well as supplying nutrients to the plant, right? So meaning that this is a measure of how much nutrient can be retained by the plant. Okay, this CEC also give an indicator of the soil water holding capacity. Because water is a polar molecules, it will be attracted by the negative charge in the soil, and it is also important in the fertilizer management. Okay, so how soil CEC is measured? Uh, I'm I just want to discuss it in brief. First, we leach the salt sample with ammonium acetate. So we use ammonium as an index cation. So what does it mean? Meaning that the measure of negative charge will be indirectly measured by the amount of ammonium that it can absorb. Okay, so first we leach with ammonium acetate and we keep the leachate and measure the concentration of basic cation in the first leachate, and then wash with ethyl alcohol to get rid of the non-absorbed ammonium, because we want to measure the total negative charge, the negative charge, by indirectly measure the ammonium. So meaning that the extra ammonium that is not absorbed by the negative charge, we have to get rid of from the system, right? And then we leach with potassium sulfate. So why? Because the potassium sulfate will leach the absorbed ammonium, right? And then we are going to measure the ammonium concentration, and the amount of positive charge from the ammonium should be the same as the amount of negative charge that absorb the ammonium. So that is the basic principle. Okay, now, so if we look at the surface charge and the CEC, so remember that, okay, we have one-to-one type clay, kaolin and serpentine. So the amount of negative charge is zero. There is no isomorphous substitution from there is no isomorphous substitution in one-to-one type clay. That is why the layer charge is zero, right? No charge coming from isomorphous substitution. But later on, we will see whether the kaolin have a CEC or not. Okay, and the 2-to-1 type clay, the first one is pyrophyllite. There is no isomorphous substitution in pyrophyllite. Okay, the surface charge is zero, but we have charge in smectite, vermiculite, mica, chloride, and peligostite, and so on. And we see there is increasing layer charge, right? So what does it mean? It means that the chloride has higher charge, higher surface charge than smectite, vermiculite, and mica. Okay. Now, let's look at the CEC. Remember, chloride have higher surface charge than the smectite, vermiculite, right? So this is one of the tables that my favorite table that I use to ask question to my students. Okay, to test their understanding on the soil CEC. Okay, so look at the chloride. So chloride, which have the highest charge, but it has low CEC, right? Kaolinite, we know the CEC is low. Why? Because there is no isomorphous substitution occurring on one-to-one type clay. But the CEC is around 1 to 10. Where is it coming from? It comes from the pH dependent charge, right? So elite, okay, elite only 10 to 40. Why elite has low? We will discuss later. And then smectite and vermiculite. So those are the minerals that have high CEC. Okay. Now, why elite and chloride have very low CEC even though the amount of layer charge is high? So the reason is because the elite and chloride, so the negative charge from elite is satisfied by the potassium cations, right? While in chloride, the amount of negative charge in chloride are satisfied or neutralized, or the negative charge bind the positively charged brucite mineral in chloride. So then, what is the meaning of cation exchange capacity? So actually, from these, we know that the cation exchange capacity is actually the measure of negative charge in soil that can hold exchangeable cation. Okay, that is the keyword, that can hold exchangeable cation, meaning that the potassium in elite and the brucite mineral in elite are the non-exchangeable cation. So it also means that even though the layer charge is high, if it held or if it hold the non-exchanging cation, then the CEC will be very low. Okay, and then I'm going to talk about the importance of CEC to soil fertility. So soil with low CEC cannot hold a lot of nutrients. All right. So because the negative charge is low, then it cannot hold a lot of positive cations. Okay. For example, the calcium, magnesium, and so on. So both nutrient holding and nutrient supplying capacity are limited in soil with low CEC. Okay. So it also, what does it mean in terms of managing the soil? So soil with low CEC, we cannot give a lot of fertilizer because they don't have the capacity to retain the fertilizer. For example, breed soil. So if we measure the CEC of breed soil, it is around, the highest probably you can get is about 4 centimole charge per kg, which is very low. All right. So sometimes we get less than 3 centimole charge per kg. So if you put fertilizer to the soil, what will happen? It is not going to be held tightly by this, not tight. It's not even going to be held by the soil. So if you put the fertilizer, most of the fertilizer will be leached down when there is rain, right? When the water seeping through the soil is going to be leached out from the soil profile. Okay, so if this soil are fertilized heavily, it will cause a lot of wastage. So consequently, polluting our environment. Okay, so soil with low CEC also need to be watered more frequently, because I already mentioned that soil with low CEC doesn't have capacity to absorb nutrient as well as water. Okay, the pH of soil with low CEC can be easily affected by the addition of acid or alkaline compound. So what does it mean? Meaning that the soil with low CEC have a very low buffering capacity. It cannot retain the pH, right? It cannot retain pH when we add alkaline or if we add acidic. So it also means that, let me see. So it also means that the soil with low CEC uh, can soil with low CEC, we can increase the pH very easily. Okay, so for example, mineral soil with low CEC, if we compare mineral soil with low CEC with peat soil with high CEC, even though they are at the same pH, let's say we want to increase from pH 4.5 to 6, peat soil with high CEC would need a much higher amount of lime compared to the mineral soil with low CEC, even though they start from the same pH, right? Why? Because the peat soil with high CEC have a more buffering capacity. So it means that it needs more lime to increase the pH, right? So on the other side, so to reduce the pH once it let's say it goes up to 6.5, so soil with low CEC, okay, soil with high CEC, the amount of time to reduce the pH of soil with high CEC, so will also be longer than the mineral soil with low CEC, right? So it means that the soil with high CEC have a higher buffering capacity. Okay, that is why nutrient deficiency usually found in plants grown in soil of low CEC standard. Okay, Dr. Rina, I will stop at 10:50. Okay, for Q&A. Just give me another 5 minutes. Okay, then another concept is the percent-based saturation. So we already measured the CEC, meaning that the amount of negative charge in soil that can hold basic cations. Okay, sorry, that can hold exchangeable cation. So now, why do we need to study or why do we need to know the percent-based saturation? The reason is because we know the negative charge in the soil, okay, which is a measure of the CC, they they can hold not only the basic cation, but they can also hold acidic cation, which are aluminium and hydrogen, right? So in general, so soil in the tropics, which are highly weathered, have low percent base saturation. Okay, so that is why our soil in the tropics are acidic. So they are more acidic compared to the soil of the temperate region. So the percent base ratio is important because the data can tell us whether the cation exchange complex, which is the CEC, I feel by acid or by the basic cation. If the percent base saturation are high, so meaning that the cation exchange complex are filled by basic cation. If the percent base saturation is low, it means that most of the cation exchange complex are holding hydrogen and aluminium, which are the acidic cations, right? Okay, let's skip this. Okay, I don't want to talk about it. Okay, let's see our Bungo series soil. So our Bungo series soil, so if we look at the pH about 4.8, okay, and then the percent base saturation, okay, the percent base saturation based on ammonium acetate is only about 70%, okay. So the CEC, let me see, the CEC permanent charge, okay, the total ammonium acetate is about 16.9. It is quite high, probably because of the presence of organic carbon. So, but look at the percent base saturation, about 17%, only about 70%. So in pit soil of Sarawak, this data from Dr. Luli, Tropical Pit Center. So if we look at the CEC, it's high, 48.7%. Okay, so where is it coming from? All of the CEC, okay, in pit soil are coming from pH dependent charge because there is no isomorphous substitution in organic matter, right? On the organic matter, there is no isomorphous substitution. So meaning that all the CEC, all the negative charge in the pit soil are coming from the pH dependent charge. So see the base saturation is only about 22.7%, right? 22.7%. So compare this data with this data. This is data from Vertisol in Kenya. So look at the soil pH. So the soil pH is 6, right? 6, 6.2 and 6.6. Okay, almost near to 7. So if you look at the amount of the percent base saturation, so it is about 63.6% base saturation. So that is why the pH is high because most of the negative charge are holding the basic cation. Okay, that is why the pH, the percent base saturation data is important to know about the pH of our soil. Uh, Dr. Arina, I think it's already 10:50. So should we stop or should I continue? Because I have a lot more to cover, but this is only
I think we can go for another 5 minutes and then we leave another
all
five
right.
minutes for question and answer.
All right.
Okay?
Okay. Okay. I'll go. Okay. Soil pH and liming. Desirable pH range for optimum plant growth varies among crops. So most of crop grow best in the range of pH 6 to 7. So others grow well under slightly acidic conditions, right? So soil properties that influence the need for and respond for lime will vary region to region. Okay, that is, and also the knowledge about the soil pH is very important. So soil become acidic. Why? Because the basic elements such as calcium, magnesium, sodium, and potassium held by soil colloids are replaced by hydrogen ion. That is why soils in the tropics are highly acidic. Why? Because of years and years of the leaching process that leach out the calcium, magnesium, and sodium and potassium. Then the question is why aluminum is not leached out, right? Even though it's a positive charge, right? So one of the reason is because in the soil itself we have a lot of aluminum, right? So we call the clay minerals as aluminosilicate clays, right? So meaning that it contains a lot of aluminum. That is the first reason. The second reason is aluminum is held very tightly by the cation exchange capacity, by the cation exchange complex. So aluminum. So if you study deeper in the soil chemistry, there is a series what we call as a lyotrophic series. Okay, the lyotrophic series which mention that trivalent cations are held more tightly than divalent cation, and the least preferable cation are the monovalent cation. So that is why that is the reason why aluminum are high even though in the acidic soil. And then uh, okay. So intensive farming over a number of years with nitrogen fertilizers or manures can result in soil acidification. So what are the effects of soil pH? First, reduce nutrient availability to plant. So this is what we have to understand. Uh, Nutrient availability, it doesn't mean that at low pH, the nutrient is not there. The nutrient is there, right? The nutrient is there, but it is not available. Why it is not available? Because most of the macronutrient will precipitate at low pH. When it precipitates, it is not in an available form. So what is the available form of nutrient in plant? It is in dissolved form. It must be dissolved in salt solution before the plant roots can take it up. If it is in a solid form, so in precipitate, in a mineral form, so it cannot be absorbed by the plant. So that is why at low pH, the macronutrient is not available. It's there, but not available. While the micronutrient, most of the micronutrient, they are very readily available at low pH. Right? How do we know this? Then you have to study deeper in soil chemistry. There is a there's a specific topics in soil chemistry. We call it as chemical equilibria in soil. Okay, which is the founder is Professor Willett Lindsay, distinguished professor at Colorado State University, Dr. Arina, and I have the honor to study in his class. Okay, so it increased the availability of some element to toxic level, especially the aluminium and manganese, meaning that at low pH, the macronutrient will not be available, while the micronutrient, which is required at very low amount, become highly available. Okay, and then acidity can degrade the favorable environment for bacteria, earthworm, and other soil organisms. So these are the diagram that that you often see uh, to describe how the macronutrient and micronutrients are available at different pH. So, as a rule of thumb, macronutrient will not be available at low pH soil, while the micronutrient will become highly available at low pH. Right? So it can become toxic to the plant. Uh,
Okay, Dr. Samsuri, I think
I have
it's
to stop.
time
Yeah.
for you
Okay.
to wrap up. So I'll give
Okay.
like 1 minute for you to wrap up as a summary, and then we'll proceed with question and answer session.
Okay. So as I said, probably I'm sorry because I cannot cover many concept in soil chemistry. So probably what I should have done is just cover on the CEC and cover in depth on the soil CEC. But I try to cover many things in soil chemistry because there are a lot of concepts that I've learned. However, I will make my slide available to everybody who require it, so you can look at through my slide and you can use it as, for your reference to understand the basic soil chemistry concepts, right? So thank you. So I'm open for question and answer. If I can answer it, I will answer it. If not, I will contact you through email to give the answer to you. Dr. Arina, you mute.
Okay, so thank you, Dr. Samsuri, for your sharing about the essence of soil chemistry in relation to soil capacity to supply available nutrients. So, from this webinar, we can conclude that soil chemistry as part of the elements to manage soils with different textures, physical, and chemical characteristics. So, now let's look at the questions we have from the viewers. So, we have one question from Dr. Christopher. So the question is for home gardeners who have no background or training in soil science. So what do you recommend is the minimum knowledge or aspects in soil chemistry they should know?
All right, thank you very much, Dr. Chris, for the question. I think what the basic layman, what the layman should do about the basic chemistry is uh, about the charge in the soil. So how can uh, uh, what are the effect, for example, what are the effect of adding organic matter to the soil? So what are the type of soil that have high CEC, meaning that have high amount of charge, and those which have a low amount of charge? For example, they should be able to understand soil which is highly sandy wouldn't have high CEC, while those soil with high organic matter would have some high CEC, meaning that have high negative charge. So, for example, we have a lot of ex-mining land in Perak, so which are composed of mostly silt and clay. They have low CEC, but they have been made productive with fruit farmings, and they are planting fruits in Perak, in Kampa, in the area. How? Because they are adding organic matter to the soil. So by adding organic matter to the soil, it improves the soil aggregation, it improves the soil structure, it improves the amount of micropores that we have in that soil. So initially, we only have the macropores, the big pores, which transport a lot of water. I mean, the high permeability of water, but they improve it with adding organic matter, which improve the aggregate stability, improve the amount of micropores to absorb water, and also it increase the amount of CEC, which have the capacity to absorb nutrients when we add fertilizer to the soil. I think that is the basic knowledge what the layman or the the gardeners say should know about the soil in regards to the charge.
Okay, thank you, Dr. Samsuri, for your sharing. So I think it's time. We're already almost an hour, right? So it's time for us to wrap up the webinar. And I would like to thank Dr. Samsuri and the Industry and Community Relations Unit of Faculty of Agriculture, University Putra Malaysia, which provide the platform to deliver the webinar. So thank you, everyone, and stay tuned for the next webinar series organized by the Department of Land Management, Faculty of Agriculture in another 2 weeks' time. Okay, so till then, take care and have a great weekend. Bye bye.
Thank you.